Structural analysis uses a mathematical model of the structure to predict the structure's response. To create the model, we need to simplify reality into an idealized version. There are three aspects of the structure that we idealize: the members, the supports, and the connections. To idealize a member, we need to consider the ratio of width to height of the member's cross-section. Structural members like walls and floors have a really big aspect ratio, and we idealize them as a flat plate. Structural members like beams and columns typically have an aspect ratio much closer to 1, and we idealize them as thin lines. When a member experiences a net internal moment, there is a location in the cross-section that has zero strain. We call that location the neutral axis. Because that location doesn't get longer or shorter, it is the best location for our thin line idealization of the member. To idealize supports, we consider which motions are restrained or prevented. If translation is restrained, a force reaction is generated in that direction. If rotation is restrained, a moment reaction is generated. Most supports fall into three idealizations. Pin supports restrain all displacements, so in 2 dimensions, they stop both horizontal and vertical displacement. That means they create horizontal and vertical force reactions. The symbol we use for a pin support is a triangle with hash marks below it. Roller supports restrain only one displacement, so they generate only one force reaction. The symbol we use is a circle on hash marks. Fixed supports restrain all motions, translations, and rotations. So in 2 dimensions, a fixed support generates 2 force reactions and 1 moment reaction. The symbol we use is just the hash marks. Connections do not prevent motion. They require that the members move together. That is different from supports, which actually prevent motion. Most connections fall into one of 3 idealizations. A pin connection makes the members translate together in all directions, but allows relative rotation. This beam column connection is an example. The beam cannot move horizontally or vertically without the column also moving, but the beam can rotate relative to the column. In the plan view, which is a drawing of the idealized structure looking from above, we draw the pin connection as a gap between the members. In an elevation view, which is a drawing of the idealized structure looking from the side, we draw the pin connection as a hollow circle between the members. A roller connection makes the members translate together only in the direction perpendicular to the long axis of the member. This beam column connection is an example. Each beam sits on a piece of column called a corbel. The beam cannot move down without the column also moving down, but the beam can move horizontally relative to the column, and the beam can rotate relative to the column. In the plan view, we show the overlapped members as dashed lines. For an elevation view, we show the connection as a hollow circle with the members not in alignment. When a connection makes both members deform in the same way for all translations and displacements, we call it a rigid connection. The column shown here is rigidly connected to the beam running across it. We show a rigid connection in plan view using a darkened triangle facing away from the supporting member. There is still a gap between the members, but the triangle is at the end of the supported member. In an elevation view, we just draw the members as touching with no special symbols. I hope at this point you are wondering, How do I know whether a connection ties rotations together or not? The reality is, all connections have some relative rotation and transfer some moment. But we idealize each connection as having either zero relative rotation, a rigid connection, or as having unrestrained relative rotation, a pin connection. In order to decide which designation to give a connection, we consider how an internal moment might be transferred. If we only connect this beam near the middle, at its web, when we try to carry moment, the bolts create a force couple with a small distance. That is not very effective for creating moment. However, if we connect the beam at the outer edges, the flanges, the distance between the forces is larger. This is much more effective for creating moment. It doesn't matter whether the connection is made with bolts or welds. The key to deciding whether to treat it as a pin or rigid connection is where in the cross section the member is held. If we connect the member only in the middle, it will behave more like a pin connection. If we connect the member on the outer edges, like these connections, it will behave more like a rigid connection.